like first to thank the organizers for having me here. It was a productive week. So as he said, I'm going to talk about the dynamics of quantum systems that have many interacting particles. What we've done was to study the time scales involved in the relaxation process of these many-body quantum systems and also their self-averaging behavior. So these works were done with Mauro Schulas and Jonathan Torres. They were both postdocs working with me. Mauro is now an editor for PRX and the professor in Mexico. So in this talk, I'll focus only on time-independent Hamiltonian. And we are going to assume that this system is very well isolated from any sort of environment. So with respect to the time scales, we are mostly interested in very long times, in the time that it takes for the properties of the spectrum to show up in this dynamics, the properties that will tell us whether this Hamiltonian is chaotic or not, whether the system is ergodic or not, and also the time that it takes for these systems to finally equilibrate. So in this program, we've been hearing about thermalization, localization, all these studies about many-body quantum systems. But an open question is how long does it take for them to reach equilibrium? Does this time increase with system size or does it decrease with system? And so these are topics discussed in this paper, and we have analytical results for chaotic systems. Now, the other subject is that of self-averaging this system. So self-average is a very important property in disordered systems. If self-averaging holds, what does it mean is that as I increase the system size, I can decrease the number of random realizations that I use. Or if an experimentalist, you can decrease the number of samples that you use. We usually take this for granted when we are doing numerical simulations, no? But that's not true. Self-average depends. You have to be careful. No? Self-average depends on the observable that you pick, depends on the model, and also on the time scale. So we haven't seen works about how self-averaging properties depend on the time scales of these many-body quantum systems. So it seems that this is a pretty new topic. And something also that caught my attention is that chaos, no? Chaotic Hamiltonians, does not necessarily imply self-average. It will depend on the quantity and it will depend on the time scales, even if I have full randomization. All right, so I don't need to say that non-equilibrium quantum dynamics is of great interest to experiments, no, with both atoms and MR, ion traps. But what I want to emphasize is that our analysis is done thinking about these experiments. Okay? So the initial state that we pick, the observables, the models, they're all thinking about these experiments. All right. So since I'll be talking about the time that it takes to equilibrate, let me tell you what we mean by equilibration, this isolated quantum system described by linear. Let me call alpha the eigenstates of a certain Hamiltonian, the Hamiltonian that is going to evolve my system, A alpha the eigenvalues. We prepare the system in a certain initial state and let it evolve. So these components here, these C alphas, are the projections of the initial state in the energy eigenbasis, not the components of the initial state. And you will see these C alphas throughout the talk. Let's pick an observable, and here we have its description with these two terms. This first term is the one that contains the dynamics, no? I have the phases, and this second term is time independent. So this one will give us the whole evolution, but after some time, we'll have just fluctuations around this time independent term, which is the infinite time average, the saturation point. So once we have just these fluctuations, that's what we are calling equilibration. Now, of course, it's important to be sure that these fluctuations are small, and more important, that they decrease with system size. And we know this is true. We are dealing with many-body quantum systems, so we don't have many degeneracies. They are perturbed very far from equilibrium, so these components are very small, and these off-diagonal elements are very small. Okay, so this is equilibration. Now, there is another interesting question, which is whether this infinite time average agrees or not with a thermodynamic average. If it does, that's what we call thermalization. That's not the subject of this talk today. All I want to know is how long it takes to reach this point. But just as a parenthesis, if you look at this, the titles of these recent review articles about thermalization, you'll see the words quantum chaos, quantum chaos. So just to emphasize that quantum chaos is the mechanism that allows for thermalization. What guarantees ETH to be valid. Very well, let's move on. I'm going to start discussing equilibration, well, the time for equilibration in chaotic systems. So let me just repeat again what we mean by chaotic systems. In this talk, what I mean by chaotic systems are just systems that will show level statistics similar to what we have in full random matrix, as we heard in the previous talk. There are other definitions, and if you want, we can talk about it, out of time order correlated. Let me simplify my life and use the traditional definition in the talk. So, eigenvalues of full random matrices, they are very much correlated. The spectrum is rigid. There are different ways to detect that. For example, by looking at the distribution of the spacing between neighboring levels. Full random matrix, we get the usual Wigner-Dyson distribution, meaning no spacing zero, no degeneracies, level repulsion. So if I see this, for our realistic systems, I'll say the system is chaotic. But of course, there are differences between realistic models and full random matrices. Not full random matrices, just matrices filled with random numbers, not physical. Realistic systems, where we have usually two-body interactions, the matrices are banded, very sparse. So where should we find differences? For example, if we look at the density of states, histogram of eigenvalues for full random matrices is the usual semicircle. For many body systems with two-body interactions, not few particles, okay, many body systems with two-body interactions, we have this Gaussian shape. The other difference shows up in the structure of the eigenstate. All eigenstates of full random matrices are just random vectors, no huge superpositions with random numbers. So this is a flat curve, that's what it's saying, that all the states are equivalent. When we move to realistic systems, then things change. It's only in the middle of the spectrum that these states are pretty much delocalized, close to random vectors, but not there yet. And it's this kind of very spread out eigenstates, chaotic eigenstates, that guarantee thermalization, that guarantees ETH. Once we go close to the edge of the spectrum, the states are pretty much localized. So this dependence on the energy, the dependence of the structure of the eigenstates on the energy, is important for studies of thermalization, equilibration, and for the dynamics. Well, localization as well. Okay, so let's questions. Yeah. What is the relationship? What I was saying is that it's important to be in the middle of the spectrum. If you get too close to the edges, the states are not chaotic states anymore. So you should not expect thermalization there. On the other hand, for localization, if you're there, it's pretty easy, well, easier to localize. Okay, so moving to the dynamics, what I'm going to do is prepare the system in a certain initial state, which is an eigenstate of an unperturbed Hamiltonian. We are going to perturb very strongly, very strong perturbation, and let the system evolve according to this new total Hamiltonian. So this is the evolution. What we are going to be doing for this talk is we are going to select initial states that have energy close to the middle of the spectrum of that total Hamiltonian. Remember, middle of the spectrum is what we were saying. We have strong chaos. And so I'm going to focus only on this region for this talk. All right. And what we are going to do is I'm going to compare the dynamics for our realistic systems with what we get for full random matrix. So what is it that we are going to do here? We have this matrix completely filled with random numbers. I'm going to assume that the diagonal determines my initial states. And then I let them evolve according to this whole matrix, completely unphysical. Nothing realistic would be described by that. But why we are doing this? Because of what I said, the eigenvalues of full random matrices are very much correlated. We know about those correlations. And the eigenstates are just random vectors. Random vectors are pretty easy to deal with. So for this case, we can get analytical results. That's the big advantage of random matrices, to allow us to get analytical results, as Wigner already knew very well. He was studying heavy nuclei. Okay, so we are going to use these analytical results for full random matrices to guide our studies for the realistic system. Examples of realistic systems, well, the disordered spin model that you've heard so much about. The unperturbed Hamiltonian will be this one. Pauli matrices in the z direction. So this is the term of on-site disorder. On each site, we have a different Zeeman splitting randomly computed and the term of interaction. What does it mean? That we have initial states such as this one. On each side, the spin points up or down in the z direction. These are the initial states that people have in ion traps. It's also the kind of initial state you can have with cold atoms. Either you have an atom or you don't have an atom. Right? So physical initial states. And we let them evolve according now to this whole Hamiltonian where we also have the hopping. So this is the Hamiltonian that was so much used in studies of many body localization, 2004 at least. We're going to start looking at the chaotic regime, as I said. So the disorder strength of the order of the interactions per related eigenvalue. Another important comment here, we have to do big averages. So averages over disorder realizations and averages over initial states. If you don't do these big averages, you don't see all the features that I'm going to describe here. So I'm going to start looking at this quantity. We also heard about it a lot in many talks before, the survival probability or return probability, the probability for finding the initial state later in time. Let's start with the results for full random matrices. Remember what I said, we can get an analytical result. So what is this analytical result? We have three terms. This bar here is the one giving us the saturation point. These other two, well, the first term has a Bessel function of first kind. This first term describes the initial dynamics. This second term is the two-level form factor that you've heard before, no? And describes the behavior this time. See, but the survival probability contains much more than just the form factor. It has this initial behavior inside it. At long times, it's pretty much similar to the form. So this expression here is the red curve. The numerics is black, so you see perfect agreement. Analytical with the numerics. Okay, now going to the realistic system, what we do is following the same steps that we had to obtain this analytical expression, we can get an expression also for the realistic system. Again, it has three terms. And this expression here is shown in this plot with the dark curve. And the red curve is the numerics. So again, you see very good agreement for this realistic system. And I want to emphasize this is really good agreement because this is a log-log plot, so tiny values here and extremely long time. And this result, this expression is not valid only for this disordered spin. Pretty general. It's valid for any many-body quantum system where we have two-body interaction and middle of the spectrum perturbed very far from equilibrium. Let me show you some examples. This is the result that I just said for the disorder model, but different system sizes. So the dashed line is this expression. Now, the other two panels, this first one at the bottom is another spin model. It has no disorder, it's clean. What we added here is couplings between second neighbors. So this is also a chaotic system. What we do numerically now, since we have no disorder, is just averages over initial states. Initial states in the middle of the spectrum, but averages over initial states. And there you see very good agreement. More fluctuations now because the averages are over initial states only. Different system sizes again. On this panel here, what we have is a banded random matrix. So no specific system behind it. Banded random matrix, very, very sparse. The level of sparsity is the same one that we have for this model. And there you have a very good agreement. So this is all to emphasize that the result is general. Another thing that I want to emphasize here is, let's talk about my components of the initial state. We are not choosing any component. We're not putting things by hand. They are coming from the quench, from the initial states, from those physical initial states that we have. The coupling parameters, I'm not touching them. As I increase the system size, I don't touch them. I don't rescale them. I do what an experimentalist would do. So no assumptions, no approximations, everything is exact diagonal. So now that I gave you this general picture, let's go for the details of that experiment. So this is survival probability. I can write it as a sum of those components of the initial state. This sum I can also write as an integral, where this rho that is showing up here is just a sum of delta functions. So if I put this back, we will recover that sum. So a sum of delta functions is just a density of states. But this one is weighted by those components of the initial state. That's why we call this local density of states, LDOS. That's what people in nuclear physics would call a strength function. So the survival probability is just the square of the Fourier transform of this quantity. So let's have a look at the LDOS. But before having a look at the LDOS, let me remove these components and look just at the DOS, the density of state, just to remind you. So for full random matrices, this is the semicircle. For the realistic system, Gaussian. If I now insert those components for full random matrices, I'm just inserting random numbers, so the shape is kept. For the realistic systems, middle of the spectrum, all that story again, no, strong perturbation, I'm pretty much just inserting random numbers again. So I keep the same shape. So you see, the shape is not universal. What I have for my real systems is not what I have for full random matrices. But on this side, things are very general, as I said. Many body systems, two-body interactions, perturbed far from the middle of the spectrum. Okay. Yes. Yeah, it depends on the sparsity and embedded random matrices. You get some kind of triangle. You may change. But two-body random ensembles, those studies that, well, since I'm in India, I should tell you, Costa has studied a lot, and embedded random ensembles, they all Gaussian. No, everything has a ramp. I'll tell you more about the ramp. You see, this is the ramp. You see here? Yeah, but they all have, it's the scale, and this is a small plot, but they all have the ramp. You see, this is the saturation point. They all have a ramp. Just that you cannot see. I should put these dashed lines for the saturation, and you will see that they all have a ramp. Okay, so what we are going to do now is just the Fourier transform of the LDOS. Fourier transform of the semicircle is the Bessel function of the Gaussian. This gamma that you see here gives the width of this energy distribution. So 1 over gamma is our first important time scale for the depletion of this initial. If we look at longer times, you will see that this dynamic slows down. So I'm longer times now. The dynamic slows down and becomes power law. I have these oscillations that decays following a power law behavior. This has nothing to do with the power law behavior as you approach localization or fractality or anything like this. Here we are deep scales. This power law behavior comes just because the spectrum is bounded. So what determines this exponent is how we approach this bound. For the realistic system, we have Gaussian tails, this exponent is 2. So this is the description of this initial behavior. So what I have in this slide is, this is the result for a realistic system, the whole evolution of the survival probability from perturbation to equilibration. This small one is the one that I showed before for full random matrix. So you see, initially, the behavior is not the same. It's not universal, that the density of states and the local density of states is not universal. But later, and now we are coming to the ramp, later I have this dip, which shows up for the full random matrices for the realistic system. This region, at this point, the dynamics became universal. And that's what I want to talk about now. So where is this coming from? Up to now, I only talked about the envelope of the energy distribution of the initial state, the shape, the bounds. But we are dealing here with finite quantum systems where the spectrum is discrete. And in our case, these eigenvalues are pretty much correlated, as much correlated as we get in full random matrices. If we take into account these correlations also, you will see that there is another contribution for the evolution of the survival probability. And this other contribution is what causes this hole on this dip. This is known as correlation hole because it's coming from correlations between the eigenvalues. It does not exist if we have like Poisson distribution. This is what people now in high energy physics is calling ramp. And the ramp because it's bringing us up to the saturation point. But this is the node idea for the quantum chaos community is just a correlation hole. So in random matrix theory, there is a function that describes correlation hole, that two-level form factor. Since I have the same kind of level statistics for my real system, I'm going to be using the same function to describe the hole for the realistic system. Now, what is done in random matrices is you just do the Fourier transform of the eigenvalues. So that's what I want to distinguish here. And these studies of form factors based only on the eigenvalues. We are not just looking at eigenvalues, because again, we are thinking about those experimentalists, cold atoms, ion traps. They don't have access to the eigenvalues like nuclear physicists. So we are doing what they could do, which is prepare the system and initial state and look at the whole evolution. If we wait long enough, then the dynamics will resolve the discreteness of the spectrum and will pick up these correlations. They exist. That's when the whole, but we have to wait some time for the dynamics to resolve the discreteness of the spectrum. So this is direct signature of level repulsion, level statistics, as in random matrix. Everything that comes before, that has nothing to do with level statistics. Fast dynamics, exponential, Gaussian, can show up also in integrable models if I have strong perturbation. Okay. That was the picture and explanation of those terms. Now what we want to do is get the time scales, the time to reach the minimum of the hole, and the time for finally saturate. So how do we get these times? I'm going to go back to our expression. The time to reach the minimum of the hole is where these two functions meet. This one is the power law trying to take us down to 0, and the form factor bringing us up to the saturation. So where they meet is the time for the minimum of the hole. And so we can get an analytical expression for random matrices, the realistic model. Pretty similar. And this D that shows up here is the dimension of the Hilbert space, and this gamma is the width of the distribution. There is a very big difference in the values that come out of this. In full random matrix, well, what is this gamma? Is the width of this distribution. So it depends on how many states are directly coupled with our initial state. Well, in full random matrix, they are coupled with all the other states. Now the matrix is completely filled. So this gamma is the square root of the dimension of the matrix. In realistic systems, we have just local couplings. So this width is the square root of L. L is the size of the chain. So what does it mean? The time to reach the minimum of the hole for full random matrix is just a constant. It does not depend on the matrix size. For a realistic system, it grows exponentially with the size of the system. So numerically, this is what I'm showing. As I increase the matrix, the hole shows up always at the same point for full random matrices. For realistic system, as I increase the size, well, it grows exponentially with system size. And how can we understand that? Well, we prepare the system in an initial many-body state. And this many-body state has ahead of it an exponentially large number of other many-body states to visit. I have an exponentially large Hilbert space. But it can only do that with local couplings. No? So from site 5, I can only go first to 4, and then from 4 to 3, gradually like that. So it takes an exponentially long time to visit all of them. Once the state has visited all of the states accessible to its energy, that's when we are going to reach the minimum of the hole. And now comes important detail. We are calling this time to reach the minimum of the hole Pauli's time. You may disagree, and then you just keep calling it time to reach the minimum of the hole. But let me try to justify. What is Pauli's time for a non-interacting system? No, it's the time that it takes for the particle to diffuse through the sample and reach the borders. What we are doing here is, since we are dealing with many-body systems, interacting particles, we are leaving real space, and we are thinking about the dynamics in this many-body Hilbert space, this spread of this initial state in this many-body Hilbert space. Once it has spread out throughout, that's what we are calling Pauli's time. I'm going to come back to this and show you more details. Hang out there. Okay, let me just now show the other time scale, which is the time to finally saturate. For this time, I only care about this function, the B2 function, because this one is already too close to 0. So I care about how this function is going to bring us up to the saturation point. At this point, the dynamics is universal, so the time that I'll get here is the same, the analytical estimate is the same for full random matrices and for realistic systems. What is it that we have here? Well, gamma is the width of the distribution. D, the dimension of the Hilbert space, is the number of states that I have inside. Gamma divided by this number is just the mean level spacing. So what we got here is the inverse of the mean level spacing, which is the largest possible time scale in our system, the Heisenberg time. What is nice is that it came directly from that expression. And then numerics again. This one grows for random matrices, grows for realistic systems. Let me put all together the two time scales. So this line, the solid line, is what we are calling Thouless time. The dashed one is the Heisenberg time, and the symbols numerics. Remember, big averages are involved and a very long time. What we see, both times grow exponentially with the system size, but the Heisenberg time grows even faster, so that means the hole is getting elongated. This is a result for the survival probability, which is a non-local quantity, global quantity. In experiments, people usually look at local quantities. So what happens if I pick a local quantity such as the spin autocorrelation function? What does it measure is how close the spin configuration at a certain time is to the initial spin configuration. And what you see is that the behavior at long times is very similar to what we had for the survival probability. This spin autocorrelation function is equivalent to the density balance that the people measure in cold atoms. So this quantity captures the whole, also the ramp and the saturation happening at long times. The behavior is so similar that we use those analytical estimates from the survival probability together with the numerics for the spin autocorrelation function, and again, we have very good agreement. So what we found here is, for the chaotic region, for these two quantities, spin autocorrelation function and the survival probability, it takes an exponentially long time for the properties of the spectrum to show up, and an even longer time for saturation to finally happen. What happens as we increase the disorder now? Move from the chaotic region towards localization. Lose correlations between the eigenvalues and now have uncorrelated eigenvalues. There are interesting things for the intermediate time scales, those power law behaviors, but let me skip that and go straight to the whole. As we increase the disorder, the whole is here. No? So as we increase the disorder, you see that it's getting postponed to longer times and shrinking until it's going to disappear. Why it's getting postponed? As I increase the disorder, well, the correlation hole detects first long-range correlation. The dynamics will detect the long-range correlations first. As I increase the disorder, I'm killing them. So the hole is getting postponed to longer and longer times. We made an analysis of how this time, which is what we are calling Thouless time, the time for the minimum of the hole, how it depends on the disorder strength. And you see that it grows exponentially with the disorder strength. It goes exponentially until it reaches the Heisenberg time, until the hole disappears. Same thing for survival probability and the spin autocorrelation function. So this ratio between Heisenberg time, the longest time scale, possible longest time scale of the system, the ratio between the Heisenberg time and what we are calling Thouless time goes to 1 as the system approaches localization. Now I want to come back to the story I said, why we are calling this time Thouless time. Again, we are using this interpretation of spreading the many-body Hilbert space. But let me come back to Thouless energy in non-interacting systems. So the Thouless energy is like the width of the resonances. Now, if the mean level space is smaller than the Thouless energy, we have diffusion. So this is the picture from real space, but you can also get the Thouless energy directly from an analysis of the spectrum. For example, by looking at the level number variance. So what is the level number variance? This is a quantity to study long-range correlations. So level spacing distribution, the ratio between spacings, they just detect short-range correlations. If you want a good picture of your spectrum, you look also at those that look at long-range correlation. So the level number variance is just the variance of the number of levels that we have in a certain interval. As I increase this interval, and if the eigenvalues are uncorrelated, the variance just grows linearly. That's what you would have when you have Poisson distribution. But if you have random matrices, if the spectrum is rigid, as I increase this interval, this variance grows much slower. It follows this log, this dashed line here. So that indicates the spectrum is pretty rigid. When we are in between the two scenarios of Poisson and very much correlated eigenvalues, when we have a realistic system, what happens is you remain on the logarithm for a while and then you escape. The point where it escapes is the Thouless energy. So below that, that's where you could explain, that's where things agree with full random matrix, that's where you have diffusion. So the point where it escapes is the Thouless energy, and this was done in studies of non-interaction. What we did was to pick this Thouless energy in this way for the interacting system, changing the value of the disorder. This was also done by Antonio Garcia. We repeated that, picked those energies, and then we compare those energies with the time to reach the minimum of the whole. And one is the inverse of the other. This gives us another justification of why we are calling this Thouless time. All right, so let me summarize this, and I want to tell you just a few words about self-averaging. So we have these analytical estimates for these long time scales. We have analytical results using random matrices and chaotic sequences. They match very well our exact dynamics. And we have this study with the disorder strength also, no? the ratio between Heisenberg and Thouless going to 1 as we approach localization, and this interpretation for the Thouless time as spread in this many-body Hilbert space. So I have 2 minutes, so let me just tell you a little bit about self-averaging. What does it mean to a quantity? When do we say that a quantity is self-averaging? When the ratio between the variance of this quantity over disorder realizations and the average square decreases as I increase the system size, which, as I said, means I can decrease the number of random realizations, which is what we usually do in studies of numerical studies. No? So let's have a summary of what we've seen. Now, as I said, there are no studies about self-averaging, how it depends on time scale, so this is new. So don't take my statements as completely general. They are based on the quantities that we studied. I think there is lots of space to understand things. I only talked about 2 observables so far, the survival probability and the spin autocorrelation function. This is non-local in space, this is local in space. But both quantities are non-local in time. And both quantities are autocorrelation functions. They are computed with respect to the initial state. So what we've seen for these quantities, so again, I don't know how general it is, but I think this is pretty general. These quantities, autocorrelation functions, they are the ones that detect correlations in the dynamics, correlations of the eigenvalues in the dynamics. They are the ones that develop the correlation hole. They are the ones that take very long times to reach equilibrium. For these quantities, in these time scales, we don't see self-averaging, even if I have full random matrix. Okay, now if we move to quantities that are local in time, such as the inverse participation ratio, which is measuring how my state spreads in the Hilbert space, or the spin-spin correlation, that's the one measured in ion traps. These quantities do not detect the hole there. So they do not detect the properties of the spectrum. And in those time scales for the whole on, these quantities are all self-averaging. Okay, so this is the story of non-local versus local in time. How about non-local versus local in space? All the quantities, the ones measured experimentally, which are local in space, yeah, so there's the last thing, that are local in space, such as these two quantities, they are self-averaging at short times, which is good news for the experimentalists. So let me just finish with the two extremes. Quantity as a survival probability is non-local in time, is non-local in space. It is not self-averaging anywhere, even when I have full random matrix. And this is the quantity that we've been seeing a lot in this program, in nuclear physics, in quantum information. It's not self-averaging any time. Now, a quantity that is both local in time and local in space, that's the best one. It's self-averaging. And that's a pretty experimental quantity. So I'm going to finish here and then go for questions. Thank you for your attention.
Remarks, questions?
Sorry, maybe I just missed it. So when you briefly spoke about banded random matrices,
Very sparse.
Very sparse, very sparse. In what connection? In which connection did you speak to?
When we were looking at the survival probability
Of
the whole evolution of this return probability, and we were comparing with that analytical expression that we. So we were studying the dynamics for that kind of matrix also, comparing with our analytical expression, and saying, look, it matches very well.
But comparing it to disordered Hamiltonian or
comparing with the expression that I got. So let me just come back to this. Okay, so this is the expression that we have to describe the survival probability. This expression is not associated with any model. I just follow the steps that we had for full random matrix, and we derived that. And then I'm comparing this expression with the disorder model, with the clean model, with the banded random.
Yeah, so you said something that at least I find surprising. So you have your thermalization time scales exponential with volume, which for non-local quantities, I believe I would not be that surprised. But then you have this unequal time correlator for local quantity. I would typically expect that it goes on with, polynomially towards equilibrium value. So why is
so that's because of what I was saying. These quantities are not local in time, so they have intrinsic memory of that initial.
Yeah, but thermodynamic quantities also, right? You compute correlator at unequal time, so that it keeps memory forever. So I don't think that those would decay exponentially.
So these quantities are local in time, and you don't see the properties of the spectrum don't show up here. The correlations between the eigenvalues, they don't show up here. Once I reach this point, I just equilibrate it. So for these quantities, like the spin-spin correlation, that quantity, it detects the correlations between the eigenvalues.
No, I understand. So I speak indeed about this one. So you have two different times. One at time 0, one at time t, and you take the. But if you think, thermodynamically, if you take in hydrodynamics, you take current, for example, energy current at time t times energy current at time 0, it decays polynomially. So I find it very surprising that you get something that decays exponentially with system size in this specific case where even, local in space, but non-local in time, as you say, yes.
But it's the same, very similar behavior to this. And this is exact dynamics. I'm not, there is approximation here.
No, I understand, but I suspect it fits in the definition of the thermalization. I suspect it is in the definition. I understand that the results are exact, right? So
okay, but since you asked, let me just say, because I get this question a lot, people ask, as I increase the system size, will this hole disappear? It doesn't. The ratio between the saturation and the hole is constant. It's different here. because for these local quantities in time, sometimes if you really zoom in, you can see a little signature of the hole, but it disappears as I increase the system size, not in autocorrelation function.
Yes.
Just a question about the correlation hole. So I'm looking at the survival probability curves. In the correlation hole regime, there seem to be some temporal fluctuations that are building up, and then all of a sudden,
No. This is just the ugly plot that I put there. Okay, I have better plots. You see that? Yeah, you're talking about this, and then
my question was, how is this related?
No, it's just the time intervals that was done for this numeric. Forget about it. It's silly. Okay, can I just say something else?
Yes.
We know the value for the minimum of the hole and the value of the saturation from random matrix. So, but this is 2 over D and this is 3 over D. So just to say that that separation is fixed.
Okay, thank you. Thank you very much.